From the top of the Sierra to the depths of Death Valley, indeed all across California, the signs of climate change are everywhere. Perhaps the most immediate change will surface in our water supply. Today, millions of Californians rely on an engineered delivery system that's being pushed beyond its limits. How we respond and adapt to those changes could be the greatest economic and environmental challenge of this century.
There's definitely skeptics, and understandably the climate system has undergone many fluctuations in the past, and there are natural drivers for climate change. But the fact is that the pace of change and the amount of change we've seen just in the last 3 decades is very, very large compared to the historical rates of change. What we have is a big freight train that is approaching us, and we need to prepare.
Predictions of potential global warming range anywhere from 3 degrees to more than 12 degrees by the end of this century. Climate change scientists build sophisticated computer models to gaze into this uncertain future.
The system is very complex, and we need some way of making quantitative predictions of how it will respond to increasing greenhouse gases and other influences on climate.
Philip Duffy, a leader in atmospheric science and climate change, helped develop many of the global climate models used here at the Lawrence Livermore Laboratory in Northern California.
If you look at one model, you could get a misleading answer. If you look at 20 different models, you can see, these really don't agree. And that's, in fact, in the case of future precipitation in California, that's exactly what you see. They really don't agree. On the other hand, there's plenty of things that you can look at in the models where they do tend to agree, and the increasing temperatures in California are an example of that.
We've seen evidence of climate change primarily through our temperature record, most notably through the minimum temperatures, where we've noticed over the past century that our minimum temperatures have climbed well over 1 degree Fahrenheit, and that trend is continuing.
More than half the rise has occurred since the 1970s. The strongest signals appear where it would normally cool off, at night, in winter, and at higher elevations. Among other things, this means a rising snow line, a troubling fact that has far-reaching implications.
There's a number of symptoms that are all kind of pointing in the same direction. These snow and vegetative indices are far enough away from urban areas that we have no doubt that this is a very large-scale footprint. It's not a local urban kind of signal. If model projections are at all accurate, we're going to see these symptoms amplify and probably accelerate.
What does all this mean? While models can't tell us specifically what will happen region by region, they do warn of a dramatically different hydrology, especially as relates to snow. Even if the total precipitation remains the same, as each storm passes through, less will fall as snow, more will fall as rain, because it's warmer, and that rain will wash off, increasing erosion, raising peak flows, and with them, the risk of flood.
The other thing that happens as the atmosphere warms, it can hold more moisture. The possibility of more intense amounts of precipitation in a short period of time increases. So both of those tend to point towards more intense precipitation and higher peak river flows and therefore higher flood risk.
But there could be an even more dire consequence of warmer winter storms. A higher snow line means less snowpack, less water naturally stored for summer demand. And the result could look like this: reservoirs virtually empty when water's needed the most.
As things change, as times change, we have less snowpack and we have increased winter runoff from rainfall. It causes more uncertainty in the models. They don't perform quite as expected or as we've programmed them to. We're going to probably operate some of these reservoirs as the snow line goes up the hill. We'll probably operate them a little bit different and may carry over more water for our winter minimums into the winter than we normally would.
Much of the state's snowpack, especially in the lower and mid-elevations, may soon be history. Projections warn of a 25% or greater loss of snowpack across the Sierra in the next 40 years. Here in the Feather River watershed, a key source of water for the state, the snowpack could dwindle an astonishing 90% by the end of this century.
If we just do business as usual, there's a potential for increased flood damages out of it and reduced water supply. We need to recognize that changing conditions require the science and engineering necessary to make predictions about a future. And it's an imperfect science. We won't know the answer every day, but the goal is to build as the most robust possible set of rule curves and operational scenarios so that we can accommodate the potential floods, but at the same time ensure adequate supplies, not only for ag and municipal and industrial, but also environmental supplies.
Less snowpack isn't the only threat to water supply. A warming climate means more variability, more extreme weather events, more heat waves, and drought. Droughts are natural in California. In fact, the paleoclimatic record shows that droughts have been much more severe in centuries past. Climate change increases the global circulation cells that encourage downward air movement over traditionally dry regions, like the Southwest and most of Southern California. Studies suggest that by the end of the century, the state may endure severe droughts every 6 or 7 years, dropping reservoirs to what managers anxiously call dead pool, a level so low water cannot be released.
Yet if you go to the drier end of things, that means you're putting greater demand on that same fixed amount that you can work with that allow you to go from year to year. So the system doesn't allow any benefit for the increased excess, but may end up with more demands placed upon it with more intense or longer periods of drought.
Sea level rise will affect the entire coastline of California, threatening real estate, infrastructure, and natural habitat. Perhaps the most dramatic change will occur in the San Francisco Bay Delta. Projections reveal just 1 meter of rise will almost double the size of the bay. Over the last 100 years, the Delta has been frozen in place with a network of over 1,100 miles of earthen levees. It is fixed. It can't adjust. It can't adjust to changes in runoff associated with climate change, and it can't adjust to rises in sea level associated with climate change. The Delta is the key to California's $30+ billion agriculture industry and the urban water needs of more than 25 million Californians. A failure in this highly pressurized plumbing system, a levee break and flood, could wipe out the critical mechanism for delivering water to demand centers all across the state.
So the way we keep it fresh now is we have to hold all those levees together, because once you open them up, salt water can move in. But the other part of it that people don't realize is that we have to tune the way we run our dams. So we store water behind our dams so that we can release that water to help keep the Delta fresh, to basically push back the salt. So a significant chunk of water that we currently store behind our dams, goes to holding the Delta fresh so we can use it as a water export facility. That part, rarely considered as one of the consequences of climate change, is first, less of that water will be available, and as sea level rises, more of that water will be needed to keep it fresh all the time.
Sea level rise will also threaten coastal freshwater aquifers. The increased pressure from an expanding ocean will push salt water inland, contaminating groundwater supplies.
Well, you're looking at the Leo J. Vanderland's water treatment facility. What it does is it takes reclaimed water treated at the Long Beach Reclamation Facility operated by LA County Sanitation District and treats that water at the highest level possible so that then we can then use it in our injection wells to keep seawater from intruding into our groundwater basin.
Rising temperatures, extreme climate variability, rising sea levels, all of these things are certain and are sure to be extremely expensive.
New research projects the cost of climate change somewhere between $300 million and $3.9 billion each year. The actual cost will ultimately depend on how much California warms and how well we adapt.